Hello, welcome to a new lesson to talk about the ideal gas. Today we want to calculate what is the function associated to the chemical potential of the ideal gas. Okay, so first we need to remember that, recall that the ideal gas is composed of particles that do not have any interaction between each other. And for this purpose, we are going to consider that we only have, one type of particle. So it is like a monatomic gas. Okay, so if we have only one species of particle, that means that we will only have just one chemical potential. So for each type of atom that composes the ideal gas, you will have a chemical potential. Okay, and this chemical potential is often labeled with the letter mu. Okay, so we are going to start by establishing a very famous equation in thermodynamics, which is the Euler equation that says that the internal energy is equal to the temperature times the entropy minus the pressure times the volume, and then plus the chemical potential times the number of particles of the system. So if we see the internal energy in this manner, we could think that it is a function of 6 variables, right? So if we think this way, we could calculate the differential of u, the total differential of u as du equals TdS plus SdT minus PdV minus BdP, and then plus mu dN plus n d mu, like this. Okay, but we know that we often consider that the natural variables of the internal energy are just 3, that are the entropy, the volume, and the particle number, right? So that means that if we calculate the differential form of this internal energy, taking into consideration that this only depends on 3 variables that are S, B, and N, from here we can establish that du is going to be T ds minus P dV plus mu dN. Okay, perfect. So if we compare these two equations, they have to be the same, right? Because we are calculating the differential of u. So that means that from here we can take a different result. So what is that going to be? Well, we see here that if we equal this equation with this, we are going to get that S dt minus B dP plus N d mu is equal to 0. Just to make this piece to match with this other piece that we have here. And this result is a very famous result in thermodynamics known as the Gibbs-Duhem relation. And that is the equation that we are going to use to calculate the chemical potential associated to the ideal gas. Because from here we can say that d mu is equal to B dP divided by N and then minus S dt divided by N. And actually what this is telling us is that, mu is a function of the pressure and the temperature, right? Because, this differential form is of the variables P and T. Okay, so we see here that we are involving the volume and the entropy, and we are speaking about the ideal gas. So for the volume, we know that there is a very famous relation that relates the volume with the temperature and the pressure, right? Which is the very well-known formula of the ideal gas that says that B is equal to nKT divided by P. So with this, we have the volume as a function of the pressure and the time, which is what we want. And on a previous lesson, we showed what is the entropy as a function of the pressure and the temperature exactly for an ideal gas. Okay, so we are going to use that function to take it into this equation, and then, we will be able to calculate the mu. So what is that result that we found? Well, we found that the entropy is equal to NS0K plus NK the natural log of T over T0 to the 5/2 times P0 over P, like this. Okay, so that is the entropy of the ideal gas, which is a very important result also. Okay, so we are going to take these two results into this d mu. Notice that when we plug the volume here, this n is going to be cancelled with this n. And then that will also happen here, right? Because we have an n as a common factor to cancel this n. So we are going to get that d mu as a function of p and t is equal to minus s0k plus k, the natural log of t over t0 to the 5/2 times p0 divided by p. And then all these multiplies are dt. And then plus kt dp divided by p. Okay, perfect. So after getting to this expression, well, we need to remember that, well, the mu is a state quantity. Okay, so that means that this represents a complete differential. And that means that we are able to take the integral on each part of the equation to get, well, the function mu that we want. Okay, but how are we going to do that? Remember that in thermodynamics, we have, well, thermodynamical processes. And that means that we are going to be from an initial state to a final state. So looking that we are working here with the variables pressure and temperature, we can say that we are having a thermodynamical processes that has a graph P against T. And, well, we can establish the initial state. For example, let's say that it will be, T0, P0, like this, and then it finishes on a final state, which is going to be T comma P, right? So you might be wondering why I wrote or why I draw this graph in this manner. Well, you're about to see why when we take the integrals, but you need to notice that when T starts changing, right, we see that the pressure stays constant. And then when the pressure starts changing, the temperature is constant. And remember that we are free to select any contour that we want, any path that we want, because we are working with a complete differential. Okay, so that allows us to calculate a contour integral in any way, right? Well, this is like a theorem for multivariable calculus that it says that tells us that we can select any contour that we want to integrate those type of quantities, and we are going to get the same result. So that's why I select this contour. So you will see it more clear right now. Let's keep an eye on this d mu. If we take the integral from the initial state to the final state, we are only going to get the function mu of p comma t minus the initial mu, which is evaluated at p0 comma t0. Okay, so I think that's very easy to evaluate. But what happens with the other elements? Well, we will have that this is equal to, and let's check this first. Looking that we are integrated on the variable p, we can say that we are on the on this side of the path, right? Because on the initial path, p does not change. So dp is going to be equal to 0. So we can only consider the integration on this side of the path. So that means that the integral is going to be from p0 to p of kt dp over p. And looking that in this path, the temperature does not change, well, that means that this t that we have here is going to be constant. Okay, perfect. So what is going to happen on the other one? Well, we have that this integral is on the variable t, and that variable goes from t0 to t. And again, from t0 to t, the pressure is constant, and it is actually equal to p0, right? So on the interval t0, t, p is always going to be equal to p0. So that means that this p is going to divide this p0, and we will get a 1 here. Okay, so this element is going to be cancelled. Perfect. So we will get minus the integral from t0 to t of s0k plus the natural log of, and we are going to take these 5/2 down here to multiply the natural log. So it will be 5 divided by 2, the natural log of t divided by t0. Yeah, like this. And this is integrated on dt. Perfect. Okay, so if we keep going, we are going to get that mu minus mu0 is equal to kt, then the natural log of p evaluated from p0 to p. And well, this is very easy to see because, well, of course, this is just going to be p divided by p0, right? So then we are going to get minus s0k, and then if we integrate with respect to the variable t, we will get t minus t0, right? Just evaluating from t0 to t. And then, well, we are going to make use of the formula that says that the integral of the natural log of x dx is equal to x minus x, the natural log of x. And actually, I think that it is like this. Okay, so we will get minus 5 over 2, right? And then x. It will be kt, the natural log of t divided by t0 from t0 to t. And then I think this is minus k times t minus t0. Okay, notice that when we evaluate this at t0, we will get the natural log of t0 over t0, but that is equal to 1, and the natural log of 1 is going to be 0. So that element is going to be cancelled. So we are going to get that mu is equal to mu0 plus kt, the natural log of p divided by p0, minus s0k times t minus t0, and then minus 5 over 2 kt, the natural log of t over t0, and then plus 5 divided by 2k times t minus t0. Okay, so from here, we are going to take the element k times t minus t0 as a common factor, and then we are going to take these 5/2 here to the exponent of the natural log to get that we can group these two natural logs, right? Recall that this is a negative, okay? So we are going to express this as p0 divided by p to the negative 1, and then this negative 1 we are going to bring it down here, right? So what is this going to be? We are going to get that mu is equal to mu0 plus k times t minus t0, that multiplies 5/2 minus s0, like this. And then we are going to factor a minus, then a kt, and then we have the same sign on the natural logs. So that means that these elements are multiplying inside of a natural log. So this will be the natural log of t over t0 to the 5/2. Remember that we raised these to the 5/2 because we took this factor into the exponent. And then this multiplies p0 over p like this. Okay, Perfect. So it is very interesting to notice that what we have here is actually the difference of the chemical potential with respect to the initial state, right? Because, well, we can see this as a mu minus mu zero equals to all this, right? But that is like the change on the chemical potential from the initial state to the final state. And we see that it is directly proportional to the magnitude kT. And remember that, well, we made another lesson, right, speaking about the entropy of the ideal gas, where we mentioned that this quantity is proportional to the kinetic energy of the ideal gas. Actually, the total kinetic energy, which is the sum of the kinetic energies of the particles that compose the ideal gas. Okay, so that I think that is an interesting fact to mention. So with this result, we can make we can get a very interesting different result from here by using the Euler equation and the fundamental equations associated to the ideal gas. Okay, first of all, we're going to remember that the internal energy of the ideal gas can be seen as 3/2 nkt. Then we are going to say that PB is equal to nkt. And again, the entropy of the ideal gas that we found on that first lesson multiplied by T, yeah, the quantity Ts is going to be T times Nk S0 plus T and K, the natural log of T over T0 raised to the 5/2 P0 over P. Yeah, just again by the result that we showed recently. And then we know that the Euler equation says that U is equal to Ts minus Pv plus mu n. Okay, so we want to construct the Euler equation from the results that we already have. We have Ts, we have Pv, and we have mu. Well, we just need to multiply that mu for an n, and then we are going to sum these three factors to get the internal energy, which is actually this element that we have here. Okay, so this is going to be, well, first of all, we are going to establish what is mu times n. So from the result that we just got, we have that mu n is equal to n mu 0 plus 5 divided by 2 minus S0 nk times T minus T0 minus nkt, the natural log of T over T0 5/2 P0 over P, like this. Okay, so now we are going to construct the Euler equation. So for the internal energy, we will get 3 divided by 2 nkt is going to be equal to, well, we are going to start by writing the element Ts. Okay, so that is nkt S0 plus nkt, the natural log of T over T0 to the 5/2 P0P, like this. Then we will have minus PV, but minus PV is minus nkt due to this equation. So that is minus nkt. Okay, and then plus mu n. So that is plus n mu 0 plus 5 divided by 2 minus S0 nk T minus T0 minus nkt, the natural log of T over T0 to the 5/2 times P0 over P. Okay, so we have this huge equation. So we see easily that this element can cancel with this element. Okay, and then you see here that we have plus nkt S0, and then we will have minus S0 nkt. Okay, so I think that element is going to be cancelled also. So like this. Okay, so after those cancellations, we will get that 3 over 2 nkt is equal to minus nkt plus n mu 0 plus 5 halves nkt minus 5 halves nkt 0 and then minus S0 nk T0. And I think that I should mention that this S0, well, it is the entropy on the initial state T0, P0. Okay, so we see here that if we sum this element with this, we are actually going to get 3 halves nkt. So that means that these elements cancel, okay? And then we can say that n mu 0 is equal to 5 halves nk t0 plus s0 nk t0. Okay. From here, we cancel the n's to get that m0 is equal to kt0 times 5 halves plus s0. Yeah, like this. Okay. But notice something. Here at the result that we got for mu, we got an element, a 5 divided by 2 minus S0, right? That multiplies a k times t minus t0. So with the result that we just found, we can take this element out from this result. Yeah, so let me bring back this equation. Okay, so this is the result that we got for mu. So from here we can say that mu is equal to mu 0 plus, it will be kt times 5 halves minus s0 and then minus kt0 times 5 halves minus s0 and then minus kt, the natural log of t over t0 5 halves p0 over p. Okay, but we know that this element that we have here from this result is equal to mu 0. So we can cancel mu 0 with mu 0 to get that mu is equal to kt times 5 divided by 2 minus s0 minus kt, the natural log of t over t0 to the 5 halves p0 over p. Okay, but from here we can say that 5 halves plus s0 is equal to mu 0 over kt0. So we are going to take that into this piece to get that mu is equal to kt, and that is multiplying mu 0 over kt0 minus kt, the natural log of t over t0 to the 5 halves times p0 over p. Okay, and just to express it in a more elegant way, we are going to say that mu is equal to kt times mu 0 over kt0 minus the natural log of t over t0 to the 5 halves times p0 over p, like this. I think just to factor the element kt to see again that the chemical potential is proportional to the total kinetic energy of the ideal gas. Okay, so I think this is the important and final result of the lesson. And recall that it is the chemical potential in terms of the temperature, the pressure, and it tells us that the chemical potential is proportional to the kinetic energy of the ideal gas. Okay, I hope you enjoyed this lesson, and thank you so much for watching.